Hello, and thank you everyone for coming to my talk about the path to a stable ABI for Rust. Hello, can you hear me? So thank you for coming to my talk. A quick introduction about myself, though I think this was already covered by our host. I'm a Rust expert at Huawei's Trusted Programming Lab in Ireland. I'm also a member of the Rust project. I'm a co-leader of the library team and also the leader of the inline assembly project group. You may know me from some of the crates that I maintain, such as Hash Brown, Parking Lot, etc. My specialty is binary translation, on which I got my PhD from the University of Manchester, and on which I even founded a startup which develops binary translation software for ARM systems. So the topic of this talk is a stable ABI for Rust. But first of all, we must answer the question, what is an ABI? What does it mean? And why is it important that it is stable? So before we talk about ABIs, we need to talk about APIs. So in the good old days, you could build an entire piece of software out of a single code base with a single team working on it and having access to all the codes. This was a long time ago, and these days, this simply doesn't scale. Today's software is made up of components, where each component is worked on by a separate team, it's from a separate organization, with little to no communication between them. Let's take an example. If you have a Linux program, this is your program worked on by your team, and it's going to call into various libraries. For example, the glibc, the C library, which is worked on by the glibc team and the glibc maintainers. And glibc itself will call into the Linux kernel, which is maintained by the Linux kernel developers. So we have a set of separate components, each of which is developed independently. The glue between these components is the API, the application programming interface. Essentially, the API defines all of the data types and all of the functions which you can use to call into a particular component. Conversely, the API also defines what is a private implementation detail of that component, the parts that you are politely asked not to rely on. And the importance of components is that you can replace them. This commonly comes up in the form of newer versions. You can if your program depends on a library, you can upgrade that library to a newer version without needing to make any changes to your program. Or in some cases, if you have a completely different implementation of that component, which has a compatible API, you can just swap it in. And this is essential for modern software design. So let's talk about Rust now. In Rust, the unit of compilation, in a sense, the component in this API model is a crate, which corresponds to a library or a binary. So a crate consists of a tree of nested modules, and each of these modules contains items. Items are private by default, however, which means that they can only be accessed by the current module and any submodules. However, if you mark an item as public, it's available outside of the module. And the most important part here is the outermost layer of this module tree, which is the crate root. anything publicly exported from the crate root is essentially available to other crates that might use this library. This is the API of a crate. Now, the API is important because it defines what is guaranteed to remain the same and what is a private implementation detail that can change at any point. In Rust, we have several very well-defined rules for this, which are generally based around the fact that if it compiles, it's stable. So let's take a function as an example. This is a public function that takes an argument, that takes an integer argument and returns another integer. If you change the signature of this function, this is a breaking change. You could have code that is passing an I32 into this function that now fails to compile. However, if you change the implementation of a function, then that's completely fine. That's not a breaking change. You've not caused any code to fail to compile. Now, obviously, within reason, your function still has to do what it is documented to do. So let's look at another example. This is a struct with two fields, one of which is a public field and one of which is a private field. The public field has a particular type, and there is code relying on that field to have this particular type because it is accessible from outside the crate. If you change the type of that field, it's a breaking change. You've caused code to fail to compile. However, what you can do is freely change the type of a private field. That's not a breaking change because it is impossible for code outside of the crate to refer to that field. Let's look at a more interesting example. What if you have a struct that only has a single public field and you add a new field to it? Is it a breaking change? Well, it turns out that it is, despite the fact that we're not actually changing anything public. The problem here is that Rust has a particular feature which allows you to construct a new struct out of its fields. That's the struct construction syntax. And it also has a destructuring syntax, which allows you to take a struct and decompose it into its individual fields. In both of those cases, you need to specify all of the fields in the struct. In this case, the struct previously only had a single field, so code could have used the syntax, and if we add a new field, we're now breaking that code. However, there is a workaround. If we add the non-exhaustive attributes to a struct, then it is a compile error for code outside our crate to use this struct construction and destructuring syntax. Therefore, it's completely safe to just add a new field to our struct. Alternatively, if a struct already has a private field, then it's already impossible for any external crates to depend on this construction or destructuring syntax because not all of the fields are available. So let's put a pin on that. Remember this. This will become relevant later on. Let's take a step back and look at the Rust compilation model. So Rust source code is represented as a set of .rs files, which are compiled by Rust into rlib files, one for each crate. And at the end, all of these rlib files are combined by the linker into a single output binary. Now, Rust has the concept of an API in Rust means that each crate defines its own API, but this is a source level thing. It means that you can replace the source code for one crate with the source code of another crate as long as it remains compatible. You'll also note that Rust requires that all crates be compiled with the same compiler versions. So what would this model look like if we had a stable ABI? So the first thing you'll notice is that instead of linking all of our crates into a single output binary, we're now compiling each crate into a separate binary artifact, a shared library, and each crate is compiled with a different compiler version. So now we still have the ability to substitute crates at the source level, but now we've added the ability to substitute a compiled version of a crate with a different one. And the interface between these compiled binaries is called the ABI, the Application Binary Interface. So why is it important to have a stable ABI? Well, let's consider some use cases. If we had a stable ABI, we could distribute compiled Rust libraries as part of an operating system. In this situation, the individual applications don't need to include their own copy of these libraries. For example, the Rust standard library. The different libraries can be updated individually from the application, which is important for security updates. You just update, if you have a security issue in one library, you just update that one library, and all of the applications using it are automatically updated. And this kind of configuration is quite commonly used in operating systems. In particular, the considered case of Android, where you have an Android application that uses the Android libraries that are already installed on the device, or a Linux distribution where you have a package manager that manages all of the libraries on the system. So another use case for a stable ABI, and I know this is a bit controversial considering this is, after all, an open source conference, but currently Rust crates can only be distributed in source code form. If we had a stable ABI, we now gain the ability to distribute Rust libraries in binary form. And this is something that is relatively common in the C world, but it's missing from Rust due to the inability to have a stable ABI. And there are a lot of companies that may be interested in investing a lot of resources in developing complex Rust libraries, but don't necessarily want to share the source code with the world. Consider something like a game engine, for example, Unity. Or maybe just use an open source one like Bevy. But I feel that it's important to allow these companies to become part of the Rust community, because in the end, the Rust community grows and develops through sheer numbers. The more people we have in the community, the more open source contributions we have. So, okay, we've seen why a stable ABI, we've seen why stable ABI is important. What would a stable ABI look like in Rust? So first of all of our library crates would be compiled to ABI stable dynamic libraries. Binary crates still, like today, get compiled to binaries. A compiled library should be backwards compatible with older versions of the same library. This means that if you publish a new version of your library, you should be able to just use it and replace an older version of this library without needing to recompile any code. Now, crates which depend on an ABI stable library should be forward compatible with newer versions of the same library. So in this case, this means that if I have an application that uses a particular library, this application must not rely on any private implementation details of that library, because those may change in a future version. So any crates that are compiled with a stable ABI must be compatible with other crates that use a different Rust C version. This is important because we want to allow crates to use the latest language features, the latest standard library features, while still being compatible with crates that were previously compiled. Now, this is particularly challenging for Rust C because Rust C needs to be backwards compatible. It needs to be able to it needs to be able to load crate to use crates that were compiled with older versions of Rust C, and also needs to be forward compatible. It needs to generate code that will be compatible with future versions of Rust C. Finally, we want to tie ABI stability to a nice and simple concept, such as API stability, as much as possible. This helps reduce the mental workload of developers, since they just need to think about a simple concept. As long as I haven't made an API breaking change, my libraries will just be ABI compatible, and I don't need to think any more about it. Okay, so these are some nice goals. So why is it that almost a decade after Rust 1.0, we still don't have a stable ABI? Well, as you can guess, it's not as simple as it seems. There are two main categories of challenges as to why the ABI in Rust is unstable. The first category is what I call implementation details. The Rust compiler that uses makes certain decisions during code generation that need to be consistent between all of the crates that are being used. For example, they all need to agree on what is the calling convention for a function, how the symbol for a function is mangled, the layout of structs, the layout of enums, the layout of trait object vtables, the format of the crate metadata, and a lot more that I haven't thought of, but will probably learn the hard way once I start looking at implementing this. The other half of the problem is cross-crate code generation, which means that the compiled code for crates tends to leak private implementation details from one crate to another. For example, the layout of types of private fields, inline functions cause code defined in one crate to be included in different crates. Generic types and functions have the same problem. So it's a difficult problem. Let's take a step back and see, well, how do other languages solve this problem? So C is a very old language, and the C standard is particularly unhelpful in terms of ABI and basically doesn't define anything. In C, you have types like int or long, but we don't know what their type is. Sorry, we don't know what their size is. Now, in practice, C is so widespread that different platforms have published ABIs based on C, which actually specify these details. So using these platform ABIs, the struct layout in C is well defined, the calling convention is well defined, symbol mangling, etc. Now, as for the other half of the problem, C programs are typically structured using header files, where the header files define the interface for a library, when the implementation of this library is actually contained in a separate C source file. The header file in C defines both the API and the ABI at the same time. Any structs defined in a header file become part of the ABI because the layout of the struct is exposed to outside programs who can then rely on this data. Similarly, any inline functions defined in header files also become part of the ABI. If any C program includes a header file that has an inline function, then that function will be copied into the program. C doesn't have any concept of privacy, which has led to several rather awkward workarounds, such as adding an underscore in front of symbols that you're not supposed to use, meaning as a polite reminder that you're not supposed to rely on these. Some libraries use completely opaque type, like the file type, which is used for file streams in C, is just defined as an opaque struct. We don't know what its size is, and it can only be manipulated via a pointer. There's also semi-opaque types, where the size of the type is fixed as part of the ABI, but its contents are hidden. C is an extension of C, which adds many features. The C++ ABI is even less defined than the C one. Instead, in C++, the actual ABI is specified by a combination of the platform ABI and the actual compiler that you're using. So different compilers on the same platform can have different ABIs. So C++ does introduce the concept of privacy. You can declare a class in a header file with public fields that can be accessed from outside and private fields. However, this kind of privacy only works at the source code level, at the API level. If you actually define such a class in a header file, the size of the class is still exposed and its field layout is still exposed. So, and therefore, its layout becomes part of the ABI, even though part of this is private. There are some workarounds that exist, such as hiding the actual implementation of a class behind a pointer, but again, you suffer the cost of a layer of indirection. Now, another feature of C++ that C++ introduced oversee is the ability to have generic functions in the form of templates. The main limitation is that these are, again, purely, is that the templates don't exist at the binary level at all. They're only a compile time concept. And therefore, any templates need to be present in header files, and therefore implicitly become part of the ABI of a library. And in fact, this limitation has led a lot of C++ libraries to just be entirely defined in header files using templates. So for a change of pace, let's have a look at Java. So Java actually avoids the problem of ABI entirely by not having one. Code generation is just moved to runtime entirely. So Java code is compiled in 2 stages. There is an ahead-of-time compiler which will compile Java source code to Java bytecode, which is a stable but rather abstract format. For example, object fields are only referred to by index. The actual runtime layout of objects is not fixed. There is a second stage where this Java bytecode is compiled to actual machine code by a just-in-time compiler at runtime. And since this happens at runtime, there's no issue of different Java classes using different JIT compilers. No, you have only a single JIT compiler that will execute the whole program, so that avoids all the implementation details issue. And since at runtime you know all the classes that are going to be loaded, the just-in-time compiler is free to do layout optimization, inlining across class boundaries, etc. The downside is that you need to be able to do runtime code generation. And that's either completely impossible on some platforms like iOS or WebAssembly, or simply impractical if you're targeting an embedded system or an operating system kernel. So a final language I'd like to make a shout out to is Swift. So Swift is a language designed by Apple that was released around the same time as Rust 1.0. And it shares many features with Rust, such as static compilation, the ability to have generics. But the main relevant feature of Swift here was released in Swift 5.0 in 2019, which is the Swift stable ABI. And Swift managed something quite impressive here, where the Swift standard library, containing a ton of generic types, about as much as Rust, allowed that Swift standard library to be shipped as part of the operating system on macOS and iOS, which significantly helped reduce the size of applications and allowed for independent updates. I'm not going to go into the full details of how they achieved this, but I just want to say that the ABI that I'm proposing here is heavily inspired by the Swift stable ABI. So shoutouts to them. Now, let's get into the actual meat of the topic. The stable. What would a stable ABI for Rust look like? So, first of all, a disclaimer. This is an exploratory proposal. None of this has actually been implemented yet. This is not an official position of the Rust project. We're still open to alternative proposals. And a lot of the details are subject to are going to be subject to bike shed. So if the syntax that I use in these slides doesn't appeal to you for whatever reason, please bear with me. So let's first talk about the implementation details, so calling conventions, symbol mangling, struct layout, etc. This is both a simple problem to address and a difficult problem to address. Okay, so the implementation details aren't defined. Just define them. We currently have a calling convention. We have a symbol mangling scheme. We have a struct layout algorithm. Just decide that this is now stable. We will never change these. Now, it's not actually that simple. We need to be very careful because once we make the decision to stabilize these implementation details, we can never, ever change them. So if we need to be very careful to not stabilize something that is suboptimal or something that has an outright bug in it. And I'd like to spend some time to talk about the create metadata format in particular, because this is a very important part of the stable API. When we build a crate with a stable API, it will produce two outputs, the actual binary and crate metadata, which is used to allow other crates to link to this binary. This crate metadata needs to be stable because it is distributed along with the library. It needs to be designed in a way that is forward compatible with so that it can be read by future Rust-C versions and is able to represent any possible future language feature that we may want to add to Rust. Again, this sounds simple, but is a hellishly difficult problem, which I am not going to get into in this presentation. Instead, I'll focus on the second half, which is the problem of implementation details leaking across crate boundaries. Consider two crates, A and B. Crate A defines a struct with two public fields, and crate B uses this struct. What is the size of the struct? 8 bytes. What is the alignment? 4 bytes. Doesn't need a drop. The offsets of the two fields are at 0 bytes into the struct and 4 bytes into the struct. What possible change could crate A make here? Because all of the fields are public, no new fields can be added, no fields can be removed. You can't change, all of the fields are public. You can't change the types of any of the fields. Really, what possible change could you make without breaking compatibility? This is a trick question. Bonus points if anyone can figure out there is one thing that you can do. Any guesses? Sorry? Not exactly. So the answer is you can swap the order of the fields, which is not a breaking change. However, it's also relatively easy to address. We can just say our struct layout algorithm just ignores the source code ordering and just sorts all of the fields alphabetically. Anyways, so the layout of foo is fixed and cannot possibly change. So in this case, it's fine for crate B to just assume that this is going to be the layout of this type and just use it directly like it does today. However, what happens if this type has private fields? Now, crate B is very confused. It doesn't know what the size of this type is because, sure, that's the layout in crate A today, but a future version of this crate could add more fields or remove some. As long as it doesn't change the public fields, it's fine. The alignment isn't known because that depends on the private fields. The drop the code that needs to be executed on drop also depends on these private fields. Even the offsets of the public fields depends on the private fields. Because of Rust struct layout algorithm will try to pack the fields together to minimize the size, the overall size of the struct. So how can crate B use this type? The solution here is since this information is not known to crate B at compile time, then make it available at runtime. So you'll note here that the struct layout algorithm has actually reordered the fields and put the bar and baz fields at the end of the struct. So in the binary for crate A, we will generate a type descriptor, which is going to be exported as a static variable symbol. This type descriptor contains the size of the type, the alignment, a drop function that is executed when the type is dropped, and niche information. We will ignore the niche information for now and get back to it later. So in this particular case, the size of the struct is 56 bytes, its alignment 8. We generate a drop function for it, and the niche information. We also export two symbols containing the offsets of the fields within the struct. Why don't we just add these at the end of the type descriptor? Well, because the order of public fields in the struct is unstable. It can change. It can be changed without it being a breaking change. So how does the code in crate B actually use this type descriptor? So the first thing we are going to do is allocate space for this. So is allocate space for the variable A on the stack. This is possible to do very efficiently. It's only a handful of instructions. And we can just use the size and alignment from the type descriptor to figure out how much space we need to reserve. The next thing that we need to do is call the new function on the foo type. Now, to call that function directly, we need to know the size and layout of the type in order to correctly compute the proper calling convention to use for this function. Since we don't have this information at compile time, what we're going to do is call an adapter function that is generated in crate A. This adapter function takes any types within this adapter function takes any types that are whose layout is unstable and passes them as arguments or return values indirectly. So as you can see in this case, the return value is the place for the return value is passed as a pointer, which is filled in by the function. Finally, we want to access the bar field on this struct. So we simply take the offset of the bar field. We read that offset from the static defined in crate A, add that to the pointer, cast the pointer to 2932, and just read the value at this offset, and then print it. Finally, we drop our foo value by calling the drop function from the foo type descriptor. So you've seen that the type descriptors are exported as a static. However, in some cases, it's not actually possible to know the layout of a type at compile time. Consider this example where we have two crates, both of which are libraries, both of which export a type. In crate A, we export a type foo. It doesn't matter what the layout of this type is, just that it's not a layout that's known at compile time. In crate B, we export another struct that uses this type foo as one of its fields. So when compiling crate B, we don't know the layout of foo. Therefore, we have no way of knowing what the layout of bar is at compile time. So despite that, we still need to export a static a type descriptor for any users of crate B that might want to use the bar type. So we solve this by essentially initializing the type descriptor dynamically when the library for crate B is loaded using a static initializer. The size, alignment, and niche information is calculated using the same layout algorithm as the compiler, taking the type descriptor for foo as an input. Then we simply emit the bar type descriptor into bar type desk, and now this is ready for use by any other libraries that depend on crate B. So let's talk about, so far we've only talked about structs. Let's talk about enums. Enums are particular because they are normally exhaustive, meaning that it is, because downstream crates are able to do a match on an enum, which needs to be exhaustive, which means all of the enum variants need to be specified. It's actually a breaking change normally to add a new variant to an enum. However, and of course, since it's a breaking change, it means that the layout of an enum cannot possibly change. It's easy. It's just like a struct with all public fields. However, if we add the non-exhaustive attributes to an enum, then this effectively disables the ability to do an exhaustive match. And this allows new variants to be added to an enum in the future. So now the layout of the enum is not known. And we handle it more or less the same way as before by generating a type descriptor for the enum, which provides its size and alignment. We export field offsets for all of the fields defined in the various enum variants. And finally, we need to expose the discriminant of the enum somehow. And Rust has clever ways of encoding an enum discriminant, which means that just saying, here's the discriminant at this offset is not actually going to work. Instead, the discriminant is exposed via a pair of functions which allow you to read the discriminant out of the enum and set the discriminant of the enum. Now, remember that niche field that I said we were going to come back to later. Well, a niche is essentially a value that cannot be represented in a type. For example, in Rust, most pointers are non-nullable, which means they can never hold the value 0. A bool value is always going to have the value 0 or 1, and it's invalid for it to have any other value. Now, this can be exploited by Rust to shorten the size of enums by encoding the enum tag in creative ways. So normally, an enum consists of a tag, which indicates which of the current variants is active, and a union of all of the fields of the different variants. Now, consider the case of the option enum, which is either some or none. A U64 is 8 bytes, sorry, but an option of a U64 is 16 bytes. You need 8 bytes for the U64, and then 8 bytes for the tag, mostly due to alignment. However, consider a box. The size of a box is also 8 bytes. However, an option of a box is also 8 bytes. And this works because the none variant is encoded as the null pointer value. Now, if we work with a type whose layout we don't know and need to work with options of that type, for example, in this case, we have a mutate function which mutates an enum of a particular type. we need to know, we need to make sure all of the crates involved agree on what is the actual layout of this option T type. And that's where the niche information from the type descriptors is used. It ensures that the layout algorithm, the layout calculations done at runtime precisely match the layout algorithm used by the Rust compiler. Okay, so far we've shown a way to make crate compilation resilient against changes in private implementation details in other crates. This works well for functions, for types, but what about generics? So generics in Rust work through monomorphization, which means that essentially when a generic function is compiled into an rlib, no code is actually generated. Instead, only a template for how to generate this function is included in the crate metadata. When this generic function is then used by another crate, this template is extracted, the generic parameters are filled in with real types, and then actual code is generated. So as you can see in this example, the makePair function is in the crate metadata for crate A, whereas the main function, which calls makePair, is in crate metadata for crate B. But once these are actually compiled to binaries, all of the code for makePair is actually only present in crate B. And the reason for this is that you can't really generate anything in crate A because you do not know ahead of time what types this makePair function is going to be used with. So this is obviously a violation of our stable ABI guarantees because the implementation of the makePair function is a private implementation detail. And we would like to make it so that if we replace crate.a.so with a different version, the updated implementation of makePair is actually picked up and used in the program. So, how can we solve this? Well, the solution is to do the opposite of monomorphization, polymorphization. Rather than generating a specialized variant of a generic function for each set of generic parameters it's used with, we're going to create a single version of the function in crate A that will work for any possible type. And the way this works is that we're going to take the generic parameters to the function and transform them into runtime parameters that take type descriptors. As you can see here, for an identity function, this function simply takes its argument and returns it, and the only information we need to do this is the size of this type. So the implementation is just a copy from one pointer to another using the size from the type descriptor. And in crate B, we simply pass, in crate B, we call the identity function with the i32 type. So we simply pass the type descriptor for i32, which is exported from the core crate, and then pointers to the input and output variables on the stack. So, okay, that's how you use the type. So generics can also be used on types. What if you have a generic type with private fields? Well, obviously we need to have a way for external crates to get a type descriptor for this type. And while for concrete types we've done this with by exporting a static. In this case, we can't really do that because the type descriptor that we're generating depends on the generic parameters. So what we instead export is a constructor function that returns a type descriptor based on the generic arguments that it was built from. The way this works is that we actually need to perform dynamic registration and dynamic creation of type descriptors. And this is a rather complex issue because it involves synchronization, it involves allocation, but it's necessary because type descriptors need to live for a static lifetime. They need to be available for the whole duration of the program. This is necessary to be able to support trait objects based on type descriptors. So in this case, we have a template which describes the struct layout, and then we pass this template and generic parameters to a standard library function that will generate a type descriptor for this type. And yes. Now, generic code can't really do much with just a plain generic type. In practice, a lot of generic code is going to make use of traits and trait bounds because these allow generic code to actually do stuff with these generic types. Consider a print function that can take any type that implements the toString trait. What we need to do here is generate a polymorphic print function, which takes obviously the type descriptor for t. We still need to know the size and alignment of a value of type t, but also a trait descriptor for the toString trait. The trait descriptor essentially is a runtime representation of a trait which describes all the operations that you can do with a trait. So as you can see in this implementation, we just call the toString function pointer on the trait descriptor, pass the trait descriptor itself as the first argument, and the pointer to the value as the second argument. Now, how do we actually create a trait descriptor? Consider this more complex example of a trait, which has an associated type, an associated constant, and a trait method. So trait methods are easy. They're just function pointers, as we've seen before. Associated constants are also relatively simple. You just embed the constant directly into the trait descriptor. Associated types are interesting. We can't directly embed a pointer to a type descriptor. And the reason is that in practice, you can easily have associated types that you can easily create a chain of associated type that extends indefinitely, which means that you need to have lazy evaluation for these. So they're instead represented as a function pointer that returns a type descriptor and a trait descriptor for any trait bounds associated with this type. So the concrete trait descriptors are associated with an impl block. For every impl block in a crate, which is an implementation of a trait for a particular type, we will export a separate trait descriptor. For example, an implementation of this trait for I32 is just going to have a simple function that returns the type descriptor for I8. The associated constant is embedded directly, and the actual method is just reading the pointer because we know the type ahead of time. Let's look at the more complex implementation of the trait descriptor. In this example, it's a generic impl block. And as before, we can't export a static for something that's generic. We instead need to export a constructor function that takes all of the generic arguments, including any trait bounds on the impl block as input, and outputs a trait and returns a trait descriptor. Again, this needs dynamic registration and needs to be, and if necessary, needs to be dynamically generated from a template. Of course, to avoid unbounded memory usage, if a particular descriptor already exists for a particular combination of types, we will of course reuse it. And this is what the descriptor looks like that's generated from the template. You'll notice that this actually includes a few extra private fields at the end of the trait descriptor, which holds the generic types. These are used as extra information, which are used by the different methods. For example, the function which returns the associated type returns information from the private fields, and the method uses the trait descriptor of debug to pass it on to the debug print function. So let's do a quick recap. To enable a so with monomorphization, there is something that you can do is take a generic function and turn it into a function pointer by instantiating this generic function of a specific type. This only works with monomorphization. You can't unfortunately do this with a polymorphic function because the information about the generic argument is lost as part of this transformation. Some SIMD intrinsics actually require compile time constants for some arguments. And these can be const generics, which again doesn't work with polymorphic functions because LLVM actually requires a compile time constant for these intrinsics and will probably crash the compiler if it's given something that's not a compile time constant. Trait specialization, which is still unstable, but requires knowledge of all traits that a type implements. That's not available to a polymorphic generic because it only receives information for traits that are explicitly specified as trait bounds. And finally, this registry of all dynamically allocated type and trait descriptors requires dynamic allocation, it requires synchronization, which is difficult to support in environments where kind of embedded or kernel environments where you don't normally have access to the standard library. Now, with that said, we still have a robust way to separate out private implementation details. However, all of these layers of indirection do come at a performance cost. For example, if we're only manipulating a type through a type descriptor, it can be very inefficient to perform basic operations. Consider this foo structure. It's an 8-byte structure. Moving it can be done using a single instruction. However, if we don't know the layout of this type, we have to do an expensive call to memcopy to move it around. And this is actually unnecessary in many cases where the crate, despite keeping some of the field private, is still willing to guarantee that the layout of the type will never change. And like it's already the case for all public fields, we provide the ABI stable attribute as a way for crates to opt in to guaranteeing that the layout of the type will never change. It effectively works by, at the ABI level, treating all fields as public. Another issue is inline functions. So inline functions can be absolutely critical for efficient performance. Consider the disaster that would unfold if something like option, the map method on option were not inlined. Realistically, yes, the implementation of map is a private implementation detail, but it's never going to change. It's always going to be the same. So we could mark this. So we could mark this function in a special way to indicate that it's never going to change, and it's fine to allow other crates to inline it. And as you can see here, it can be done with by specifically opting into it with the inline export attribute. A normal inline function still has its implementation considered as a private implementation detail and is therefore not actually inline when compiling as ABI stable. However, if you specifically opt into it, then we'll allow it to be inlined in downstream crates. Now, an inline function being defined inside the crate is able to access private fields. However, this needs to be done very carefully because anything that an inline function accesses implicitly becomes part of the ABI. So the solution here is to avoid accidentally making huge parts of a crate part of the ABI, is to restrict exported inline functions to only access fields that are either public or that have been specifically marked as being ABI stable. So this can be done at the whole struct level, in which case the whole layout of the struct is fixed, or at the field level, in which case the offset for this field is exported just like a public field. Now, so far we have a system that makes that makes crates resilient against changes in implementation detail. But we also want to have the ability for an API to evolve over time, to add new features. And when doing so, we need to know, we're basically allowed to make any change that is not considered a breaking change. So the cargo book has a page about this that goes, it's the page on semantic versioning, if anyone's interested, that goes into a lot of details of exactly what is and isn't a breaking change. But for example, you can add a new public item, that's fine, but you can't remove something that was previously public. You can add a public field as long as the struct is non-exhaustive, but not if it's exhaustive. You can reorder the fields in a struct, etc. But I'll just want to concentrate on the last four. It's not a breaking change at the API level to remove the last private field from a struct. It's also fine to reorder items in a trait. It's also fine to relax the generic bounds on the trait impl, or to just remove the non-exhaustive attributes. However, at the ABI level, these actually become breaking changes. Reordering items in a trait changes the layout of a trait descriptor. Changing the generic bounds in a trait dimple changes the arguments passed to the trait constructor function. Removing the last field from a struct or removing non-exhaustive changes a struct from being used indirectly to a type descriptor to having that struct be directly exposed, which changes the way it's passed in calling conventions. So these rules are quite subtle and can be hard for a human to follow. So we need tools to help the humans avoid making mistakes. So thankfully, it's actually rather easy for a computer to verify that these ABI rules are being followed. Now, a tool already exists for checking API stability. It's called SemVerver, Semantic Version Verification. And this could be extended to also check that the ABI of a crate hasn't been broken. Now, if in the future we have a compiled crates repository similar to crates.io but with binary crates, this could even be done as part of the publishing process, where cargo publish binary would actually verify that the new compiled binary that you're uploading is actually ABI compatible with the one that is already in the repository. So, in conclusion, we've just presented a possible path to supporting a stable ABI for Rust, which allows individual Rust crates to be substituted and upgraded after being compiled. By allowing this, by allowing the crates to be distributed in a stable binary format, this opens up many new opportunities for the Rust ecosystem. And finally, we look forward to further developing this proposal and working with the Rust community to develop this feature into something that can be useful for everyone. Thank you.